In 2025, China built 157 kilometers of highway without a single construction worker lifting a shovel. 10 autonomous machines worked in formation while human supervisors observed from control rooms. Each machine made thousands of independent decisions every second, guided by sensors and satellites that offered accuracy down to the centimeter. The result was the first large-scale highway project in history completed almost entirely by artificial intelligence. What unfolded on the Beijing-Hong Kong-Macau Expressway was not just another milestone in infrastructure but a glimpse into how the physical world may be built in the future. The Golden Channel. The Beijing-Hong Kong-Macau Expressway is one of the most important transportation routes in Asia. Known as the Golden Channel, it links the manufacturing centers of the Pearl River Delta with the economic and political hubs of the north. Every day it carries millions of vehicles, from heavy trucks transporting raw materials to passenger buses and private cars. The road is more than asphalt and concrete. It is a lifeline that sustains trade, connects families, and drives the growth of entire regions. Yet it has also been the scene of chaos. In October of 2015, during the National Day holiday, more than 750 million people were on the move across China. At one toll station, 50 lanes of traffic were forced into just 20, and the result was one of the worst traffic jams ever recorded. Cars stood motionless for hours as far as the eye could see. From helicopters, the jam resembled a frozen river of steel stretching to the horizon. News outlets around the world called it Carmageddon, and the images became a symbol of the strain placed on modern infrastructure. For Chinese leaders, the event was not simply embarrassing. It revealed a deeper problem. The nation's infrastructure was modern yet still vulnerable. The scale of demand could outpace the ability of human labor to expand and maintain road networks. Traditional methods of construction required large numbers of workers, long schedules, and constant risk of delays. Even with massive investment, the speed of building was not enough to keep up with the pace of growth. The 2015 disaster became a turning point. If China wanted to sustain its development, it would need roads that could be built faster, smarter, and with more precision than human hands could provide. That idea planted the seeds for a new approach to infrastructure. Rather than relying on larger workforces, engineers began to explore whether machines could take on the tasks of paving, rolling, and compacting asphalt. China already led the world in using automation in ports, factories, and logistics. Extending artificial intelligence into construction was ambitious, but it offered a possible solution to the bottleneck exposed by Carmageddon. Over the next decade, research and testing focused on creating machines that could operate without drivers, coordinate with one another in formation, and respond to real-time data with accuracy that surpassed human judgment. By 2025, the vision was ready to be tested. The Beijing-Hong Kong-Macau Expressway was chosen as the proving ground, and 157 kilometers of road would be built almost entirely by autonomous machines. The project was not only about completing a stretch of highway but about demonstrating that infrastructure itself could enter a new era. When the 10 machines lined up at dawn on the opening day of construction, they were not symbols of replacement but of transformation. They represented a shift from muscle and instinct to sensors and algorithms, and they carried with them the promise that future roads might be built with speed and precision once thought impossible. How did 10 machines working in formation replace an entire human workforce with such precision? The robotic crew. When construction began on the Beijing-Hong Kong-Macau Expressway, the site was unlike any road project the world had seen. There were no teams of workers in reflective vests guiding machinery, no foreman standing in the dust shouting instructions, and no drivers perched inside heavy vehicles. Instead, 10 massive machines lined up in formation, each one guided by an artificial intelligence system that operated with millimeter accuracy. Human supervisors sat in remote control centers, watching the process unfold on screens filled with streams of live data. At the center of this robotic team was the SAP-200C-10PA, a paver so advanced that it could spread for full lanes of asphalt in one pass. Its screed stretched 19.25 meters, wide enough to cover the entire width of the expressway. Moving forward, it laid down a continuous ribbon of hot asphalt, the surface glowing as heat shimmered into the morning air. To observers it looked almost like a mechanical whale gliding along the roadbed, its bulk hiding the complexity of sensors, processors, and hydraulic systems working in perfect sync beneath the steel exterior. Behind the lead paver followed the rollers. They were organized in what engineers called a 1+3+3+3 formation. The single paver led the way, followed by 3 groups of rollers. The first group consisted of 6 double-drum steel rollers, each weighing 13 tons. Their job was to press the hot asphalt while it was still soft, smoothing it into an even layer. The next group included 3 enormous 30-ton rubber-wheeled rollers that provided the final compaction, pressing down until the surface achieved uniform density. Watching the formation in motion was like watching a choreography designed for machines. Each vehicle adjusted its speed, distance, and pressure automatically, responding to signals not from a human driver but from the constant analysis of data. What set this project apart from earlier experiments in automation was the degree of autonomy involved. These machines were not simply following pre-programmed routes. They were making thousands of micro-decisions every second. The paver adjusted its screed angle if it detected a variation in the roadbed. The rollers increased or reduced pressure depending on the compaction of the asphalt beneath their drums. Sensors measured temperature, density, and alignment in real time, feeding information into algorithms that learned as the work progressed. Humans monitored but rarely intervened, stepping in only if a malfunction occurred. The precision was made possible by China's Beidou satellite system, which provided centimeter-level positioning. Combined with radar, lidar, and infrared sensors, the machines could detect their environment with remarkable clarity. They knew exactly where the edge of the pavement lay, exactly how much pressure was needed to eliminate a soft patch, and exactly how fast they needed to move to maintain uniform quality across the full width of the highway. To engineers who had spent years training human crews to achieve consistency, the sight of machines delivering perfect compaction without hesitation was astonishing. Safety was a major concern. Traditional construction sites are among the most dangerous workplaces in the world. Heavy equipment, extreme temperatures, and constant noise create an environment where accidents are common. Removing human operators from the immediate area reduced that risk, but it also required new layers of protection. Each machine carried electronic fencing systems that projected invisible barriers around its moving parts. If an obstacle entered the zone, the system triggered an automatic stop within milliseconds. Cameras and radar scanned for hazards, while communication networks linked the entire crew so that if one machine paused, the others adjusted instantly to maintain formation. One of the most impressive achievements was a technique known as zero-edge rolling. Human operators often struggled to compact asphalt at the very edges of a road without damaging curbstones or leaving gaps. The autonomous rollers solved this by using advanced tracking algorithms that allowed them to follow the pavement edge with millimeter precision. The result was a seamless surface that required almost no correction afterward. Engineers who inspected the finished lanes reported that the edges were among the cleanest they had ever seen. The technology inside each machine represented years of development by SANY, China's leading heavy machinery manufacturer. Engineers faced problems that had never existed before, such as teaching a roller to sense whether asphalt was properly compacted. They developed what the company called fusion self-sensing high-precision positioning. This meant combining data from multiple sources, infrared heat sensors, pressure monitors, GPS signals, and cameras into a single understanding of the environment. The machine then made adjustments automatically, blending all the inputs into a decision-making process that functioned faster than any human crew could manage. The efficiency gains were clear. Traditional highway construction required dozens of workers across multiple shifts. Crews needed breaks, coordination, and constant supervision. Machines, on the other hand, worked with consistency hour after hour. They did not tire, they did not deviate from formation, and they did not require complicated handovers between shifts. This not only reduced labor requirements but also increased the predictability of outcomes. A project that might have taken months could now be completed in a fraction of the time, with fewer defects and less need for rework. From the perspective of the supervisors watching from control rooms, the machines resembled an orchestra of steel instruments. Data screens displayed temperature curves, compaction readings, and positional maps. The supervisors could intervene at any moment, but more often than not their role was to observe rather than control. Each kilometer completed generated more data, and this data was immediately stored for analysis. Engineers could then refine algorithms, improving performance for the next section of road. In this way, the machines were not only building a highway but also teaching themselves how to build better in the future. Observers noted the uncanny calm of the construction site. Where human crews usually produced a constant background of voices, engines, and metallic clatter, the autonomous crew moved in near silence except for the low hum of engines and the hiss of asphalt being spread. Without the chaos of workers moving between machines, the site looked almost sterile, more like a laboratory experiment than a construction project. Yet in that calm efficiency lay the promise of a new era, one where infrastructure could rise with less disruption and far greater consistency. The success of the robotic crew on the Golden Channel was not simply a technical achievement. It was a statement about the direction of construction itself. For centuries, building roads required immense human labor, from the stone paths of ancient Rome to the sprawling interstates of the United States. Now China had shown that machines could take over nearly every aspect of the process.